Hi, I'm Fernando Pereira from UFMG, and today I will show to you a few techniques that we can use to improve range analysis in both time and precision. The first thing that we should consider is that our widening strategy is a bit too hasty. We apply widening too early, and that hurts precision. For instance, consider this program on the left. Its constraint graph appears on the right. What would be the ranges of variables too long 0 and too long 1? If we simply apply our growth analysis, then there are two possible results. If we start propagating ranges from the constant 0, then we end up with these ranges that you can see on the bottom of the figure. All the variables go from 0 to plus infinite. You can try it yourself. Just stop the video, pick up a paper and a pencil, and see how growth analysis does in this figure. And there is no narrowing that we can do because we don't have any intersection to narrow the ranges. This result is clearly imprecise because either variable can only be 0 or 1 in truth. If we iterated twice before doing widening, then we would get this result, the interval 0, 1 for each variable, the most precise result. But this approach does not work always. It's possible to come up with programs that force any number of iterations before we stabilize. But there is a nice heuristic that we could use. It's called jump set widening. Basically, instead of widening to either minus or plus infinite, we widen to some constants. The question is, which constants? The most common implementation of jump set widening simply collects all the constants that appear in the program. In this example, we have two constants, 0 and 1. So instead of widening to plus infinite, first we widen to the next constant, in this order, 0, 1, and then plus infinite. In practice, we are using a somehow different lattice to implement our growth analysis. That's the lattice that we're using on the right. And in this case, we get exactly the tight interval that we want for each variable. Both too long 0 and too long 1 will be bound to the interval 0, 1. One very interesting fact is that the strong components help to improve not only the running time but also the precision of our implementation. For instance, consider this constant graph, which I took from our running example. If we applied growth analysis on the entire graph instead of on strong components one each time, then we would end up with these intervals. This is before narrowing, actually. The problem is that once we reach the component of variable j, down here, we are propagating very loose intervals to j0. j0 will be 1 plus infinite. And that causes the other variables to be bound to the most imprecise interval, which goes from minus infinite to plus infinite. However, if we solved the first component before moving on, if you solved components once each time, we would get that k ranges from 1 to 100. That's what we get out of the combination of widening and narrowing. And then j0 would be 1, 100, instead of 1 plus infinite. And with these better ranges, more precise ranges we would get much tighter limits for the variables in the j component. So given the way that we have implemented our analysis, we need to apply the widening and the narrowing operators per strong component instead of one for the entire graph, instead of once for the entire graph. Otherwise, the analysis still terminates, but it's not very precise. Here I have a few results to show you considering an actual implementation of range analysis for the LLVM compiler. The figure contains 32 dots. Each dot is a different combination of features of range analysis. Notice that these plots relate precision on the y-axis and the running time of the analysis on the x-axis. Precision is measured as the number of variables with constant bounds in millions. Each dot contains the results for all the programs in Spec CPU 2006. For instance, if we go from SSA to eSSA, we always improve precision. The blue boxes separate the analyses that run on SSA form programs, and the red boxes above show the analyses that run on eSSA form programs. As you can see, we are gaining precision without increasing running time. In truth, conversion to eSSA from SSA is super fast. And if you run the analysis interprocedurally, we gain some precision, but the running time increases a bit too. Context sensitiveness, in turn, does not improve the analysis much. It does not improve precision, but it increases the running time quite a bit, at least in this implementation. One last thing that I should mention before we finish for today is that our approach to range analysis is pretty conservative. It runs quite fast, but the results are not very good in general. For instance, consider this program. What would be the range for variable s? Would you like to think about it? Just stop the video and think about what would be the range of variable s. To help you, I'm giving you the control flow graph in eSSA form on the right. You can again stop the video and try to find the range of the variables in this control flow graph. Just grab a piece of paper and pencil and then you can try to do it. But well, in this example, we end up assigning the range 0 plus infinite to s. That's unfortunate because s clearly has the same range as variable k. If we come back here, s and k, they're growing together. However, we have a condition bound in the range of k and no condition bound in the range of s. What happens is that our range analysis is not relational. In other words, it does not associate information with pairs of or sets of variables. We cannot find any relation between variable j and k in that example. There are stronger analyses that would be able to find these relations. They are called, as I said, relational analysis. And with this last observation, I close this class on range analysis. The implementation that we had seen comes from this paper down here, a fast and low overhead technique to secure programs against integer overflows, which was published in CGO in 2013. Thank you.